Okay, so this is chapter 10, question number 12. So they give you 2-point masses, okay, and they're attached by a light stick, so the mass of the stick is negligible, okay. You let go of the system, and they want to know the magnitudes, meaning they don't care about the direction, they don't want a plus or minus. They want the magnitudes of the initial accelerations of particle number 1 and then particle number 2, okay. Now, they're asking for the acceleration. Okay, so in this chapter, that word is the letter A. It's the vector A. And there's a radial acceleration and a tangential acceleration. Well, the radial acceleration, that's just v squared over r from our earlier chapter. Okay, and as soon as this thing is released, it's not moving. Okay, so initial speed v, the linear speed of the masses are 0. So the radial acceleration, 0. So all you have left is the tangential acceleration, okay? And we know that tangential acceleration is r alpha, okay? Well, we know the distance out to each one, but we don't know the angular acceleration when you let go of the system. So that's why we use Newton's second law written in terms of torque, okay? So Newton's second law for rotation. So solve this for alpha. So you need to calculate the torque and the moment inertia, okay? Moment inertia is no big deal because they're point particles. Just do sum of them r squared, okay? But the torque, okay, you have to pick an axis about which to apply torque. Okay, so I'm picking, that's my axis A, that one right there. Okay, and then I know that since the masses are the same, this system is going to rotate the way we're looking at it. It's going to rotate clockwise. So I'm choosing clockwise as my positive direction for torque. Okay, and remember torque, force times moment arm. Okay, so Newton's second law, net torque is I alpha. So since clockwise is positive, I look to see which object's force applies the clockwise torque. So this is number 1, this is number 2. Okay, so number 2, okay, M2G, okay, exerts a clockwise torque. So there's the force M2G, okay, I'm just calling it M, okay, because the masses are the same, and its moment arm is L2, and then number 1 exerts a counterclockwise torque, so its torque is negative, okay. And then moment inertia, I just sum mr squared. So there's mass 2, distance out to number 2 squared, okay, from the axis rotation, mass number 1, distance out to mass number 1 squared, okay, times alpha. And then just cancel out the m's and solve this for alpha. So I put in the variables, and it gives me the angular acceleration, okay. And remember, that's for any part of the stick, okay. So obviously not the axis, but any point on the stick has the same omega, has the same alpha, okay? All right, so I'm trying to find the acceleration, which is my tangential acceleration. So I know all the r's and I know alpha. So for number 1, the one on the left, A tangential is L1 alpha. So there's my L1, there's my alpha, and same for number 2. Okay, so in the picture, when you let this go, A tangential 2 is down. Okay, that's going to rotate like that, and A tangential is up, but they just want the magnitudes. Okay, for number 14, okay, there's my system. So I have a rope wrapped around a hollow spherical shell, like a basketball, okay? They give me a pulley and a mass. Now, what you have to be careful in these problems is they tell you the pulley has rotational inertia I. So you can't assume, okay, you can't assume that that pulley is a disk, okay? It doesn't tell you it's a disk. So you can't write, okay, you can't write I is 1/2 mr squared, okay? Because looking at it, it's not a disk. It's got this little edge here, okay? So they just tell you the moment inertia as a number, so you're stuck with that, okay? That's not a big deal. Okay, so you let the system go, and both of these things are going to rotate, and the block is going to head toward the floor, and they want to know how fast is it going. V equals what after it's gone 1.06 meters, okay? Okay, that's an energy problem, because with respect to the floor, initial energy in the system is potential energy of the block, okay? And you let that go, and all potential energy of the block gets converted into translational kinetic for the block and rotational, okay, rotational for the sphere and the pulley. Okay, so it's an energy problem. Okay, so what you do is you have to define your system, because if I just look at the shell, okay, initial energy is 0, final energy is not 0. It's rotating, has a rotational kinetic energy. So energy is not conserved for the sphere because that tension does work. Okay. Same thing for the pulley. Tension does work on the pulley to speed it up, and this tension does work on the little mass to prevent it from being in free fall. Okay. But if you take this dotted line, okay, you take this whole a collection of three things, and the Earth to be your system, then those tensions are internal to the system, and the work done by those tensions, the net work done by those tensions, is 0, because the tension is an internal force. So there are no non-conservative forces that do net work in the system, no energy loss or friction, so E initial is E final for the system. Okay, and then so I just picked my reference point for potential energy. That's when the number one, or the block gets to the floor, and then I have to write down each energy term. Okay, so I wrote down both kinetics, okay, for number 1 potential, both kinetics for number 2, okay, which I didn't really need to do because number 2 isn't something that rotates, so I didn't need to write it down. Nothing wrong with that. Okay, and then for number 3, okay, I wrote down kinetic and potential for number 3. Now I didn't even really need to consider potential energy for number 1 and number 3. Okay, because they're spheres. Okay, they're not moving anywhere. Their gravitational potential energy is not changing. So I just put it anyway. So for the final, I have final for final kinetic energy for number 1, potential, okay, and so on. So this is all for number 2. That's all for number 3. Okay, and then I just went term by term. Okay, that's 0. Okay, because nothing starts out rotating. Okay, nothing starts out moving. Potential number 1, okay, essentially I'm picking a reference point here, right? Potential energy is 0 for number 1, and then I could say over here potential energy is 0 for number 3, but these things aren't moving up and down, okay? So their potential energy doesn't change, so there is no reason to even write those potential energies. Okay, so number 2 is not rotating, number 2 is not translating, okay, but number 2 does have potential energy, okay, so I wrote that, M2GH, okay. Number 3 is not initially rotating, number 3 is not initially translating, and number 3 has no initial potential energy, okay. So I only have one term on the left, okay, so the only energy in the system is potential of the block. Then I let the system go, okay. So the block, when I go through all of these terms, so 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Okay. The only thing that I have that's non-zero is I have the rotational kinetic energy of number 1 final. Okay, that's the sphere. And then I have, right, I don't really need to write that because number 1 is a sphere. It's stuck. It's not translating anywhere. Okay. And then this one here. Okay, that's the translational kinetic energy of the block. Okay, and then potential energy of the block final hits the floor, that's 0. And the only other thing I have left is the final rotational kinetic energy for number 3. Okay, that's the pulley. Okay, okay. Now the problem is I'm trying to find V. Okay, I need a V, but I don't know omega 1. I don't know omega 3. Okay, so I have my picture here again, and I have to make the connection between what the speed of the block is doing, okay, what the speed of the block is doing, and what these omegas are doing, okay. So instead of calling this omega 1 final, okay, and this one omega 3 final, okay, I just got rid of one subscript and just called this, I just called that omega 3. Okay, that way I have one subscript instead of 2 subscripts. Okay, so as the block heads to the floor, okay, and we did this in the notes, the speed of the block is the same as the speed of the string, okay, which is the same as the linear speed of the rim, okay, but the string doesn't stretch, and that's the same as the linear speed of the rim for the sphere, okay. So I made a connection between what the speed of the block is, okay, what the block is doing, and what the rims of the pulley and the sphere are doing. Okay, so the speed of the block, okay, is equal to the linear speed of the rim number 3, that's r omega 3, and the speed of the block, okay, is equal to the linear speed of the rim of the sphere. Okay, that was the pulley. Okay, this is the sphere. Okay, and r omega for the pulley is for the sphere is capital R omega 1. Okay, so I just solve each of these for omega. Okay, so here's omega 1, there's omega 3 from that one, and then I'm going to put that omega 1 into there. Okay, it's going to go right there, and then for omega 3, I'll put that one right there. Okay, and that's what I did. I just rewrote this whole thing. I put in what I is. Okay, so I1 is a shell, so look that one up in the book. It's 2/3 mr squared. Okay, and then for I3, they just give you the number. Okay, so I just did the algebra, right? The r's here to cancel. Okay, and then solve for v, and then I think they give you everything in the correct units. So that gives you the speed of the block.